Welcome to a demo on the Temporality extension for the Web Feature Service standard in the OWS-9 testbed. What was the motivation behind extending the Web Feature Service and filter encoding standards? Web feature and filter encoding standards have proven their suitability for many domain models based on static features. However, in the course of previous OWS testbeds in the aviation domain, it turned out that support for dynamic feature data such as AIXM is limited. Dynamic features are very different in some aspects from static features. Whereas the state of a static feature is fixed, the state of a dynamic feature is subject to change and tracked through time slices. In simple terms, each time slice models a change in one or more properties of the feature at a specific point in time. Thus, the number of time slices of a feature directly correlates with the number of changes and the lifetime of the feature, which can be huge in an operational setting. To derive a complete state of a feature at a specific point in time, a number of time slices have to be aggregated to a single one, called a snapshot time slice, by following the rules defined by AIXM. What are the key limitations for the existing standards regarding dynamic features? One of them is the lack of suitable operators to filter time slices. Without, clients always receive the full history of time slices for every feature in a result set, which is not what is usually demanded. What is missing is the ability to request a subset of the feature's time slices. In particular, the powerful filter encoding operators cannot be used for that. For dynamic features, state generation should be supported by the Web Feature Service. State generation is a complex task for AIXM features, as it involves the aggregation of time slices and sometimes also the evaluation of properties with schedules. The ability to create a snapshot for a feature is useful for any Web Feature Service serving data based on the GML dynamic feature model. There are two advantages in letting the service calculate the state of a feature, then to burden the client with it. First, performance in space, as less data needs to be transmitted, and second, less redundancy of implementation, as usually there are multiple client applications accessing a Web Feature Service. It is common practice to move the complexity to the service, if useful for several clients. Another limitation of the existing standards is the little support for time-based constraints, which are of special importance for dynamic feature data. Here's an overview of the functionality that is added to a Web Feature Service request. A new parent element called Dynamic Feature Query is introduced, which replaces the legacy query element. This element is necessary to accommodate the new projection clauses and filter elements. One of the new projection clauses is snapshot generation. If present, the features returned contain the complete calculated state at a given point in time. If the client wants to apply filter criteria to the list of time slices, it can do so by adding the projection clause timesliceProjection. It contains a filter element from the filter encoding standard. Filter on feature level can be defined in the dynamic feature filter element, which replaces the legacy filter element. Time-based constraints can easily be defined by adding a time indicator element to that filter. Here's a demonstration of what clients can achieve by using the new snapshot generation query functionality. Visual clients, such as Luciad's aviation client, are enabled to retrieve the state of an AIXM feature without having to evaluate the AIXM temporality model. In the background of this client, a getFeature request on a runway element is submitted to the Temporality-enabled Web Feature Service. It contains a dynamic feature query with snapshot generation enabled. The response contains a single time slice with the full information on the runway element. The client is relieved of the aggregation of multiple delta time slices according to the AIXM temporality model. If a property is changing on a regular basis, the client can optionally choose to have the schedule definition evaluated at the given point in time, which further reduces the complexity in the client implementation. In summary, snapshot generation allows much thinner and simpler clients to interact with dynamic feature data and saves communication bandwidth. In the next demo, the ability to request a subset of time slices is demonstrated. The use case example chosen is flight planning. Here, an AIS officer may want to request all airports in a certain area with specific criteria, for example to allow big planes such as A380 to land. As the flights are planned, he or she is only interested in what airports are suitable in a period of time in the future. For this, it suffices for the client to retrieve the baselines of the airports temporarily intersecting with a given time period and fulfilling certain criteria. The response is a subset of baseline time slices, which allows the client to display the match easily. Again, calculation effort on client side and bandwidth is saved in comparison to a non-temporal web feature service. What accomplishments were made in the process of creating the extension? At the beginning, common use cases in the aviation domain were identified. Different areas of application were examined, among them visualization, decision support, AIP publication, and NOTAM communication. Next, technical requirements were derived from the use cases and mapped to web feature service requests. Missing functionality was generalized to form a solid base for an extension, which in turn was embedded in the abstract model behind the web feature service and filter encoding standards. Finally, the model was used to generate a physical representation in form of an XML schema, and a prototype was implemented and tested, both on server and client side. Here's a summary of what we've seen and learned. It was proven that OGC standards, in this case web feature service and filter encoding standards, can be extended to support dynamic features, including the specifics of the AIXM temporality model. The temporality extension enhances the power of the query language, especially for retrieving AIXM data. It's also suitable for managing dynamic feature data in general, and thus is applicable to other domains too. It is ready to reach the next level in the OGC hierarchy of papers, an OGC best practice. Further, more detailed information can be found in the following documents: the WFS Temporality Extension Engineering Report and the WFS Temporality Extension Discussion Paper. Thank you for your attention.